last talk of the first session is Jordan Marajg. So Jordan Marajg is a postgraduate researcher in the School of Mathematical Sciences at Queen Mary University. He is in his 4th year, so soon to be hopefully crossing the line of getting a PhD. And he also got his first degree at Queen Mary University. So his research interests lie in general and mathematical relativity. So go for 35 minutes.
Yes. So, good. Okay. Well, thank you very much for the invitation to speak at the Black Heroes of Mathematics, and thank you for the organizers as well for putting together such a lovely session once again. All good. Lovely. So yes, I'm Jordan. I'm going to be talking to you about some of the stuff that I like to do and probably weave in a little bit about me as I go through. So yeah, this is my title. It's A Mathematician's Perspective on Modeling a Space-Time Scattering Problem. By the end of the talk, you'll probably have a flavor for what the hell that means. Hopefully. We'll do a comprehension test at the end. All right, so first off, 2 tales. So 2 stories. A long time ago, in a galaxy far, far away. So Kieran, could you pull up the link here? I wonder if this will work. Okay. Good. Oh, you can hear, you can hear. Has anyone seen this before? Yes, okay, got a couple nods, So this was the first detection of gravitational waves in 2015, but they put a noise on it.
There's a type of wave so mysterious and so powerful that for centuries it was the stuff of legend.
They did it better than me. No, but this is true. This is true. For 100 years, basically, we didn't actually know that gravitational waves existed. 2015 comes around and then they say, hey, we finally found one. The detectors were running for maybe 25 years with nothing. And then they finally got one. So it's been 10 years since then because it was detected in September of 2015. So it's very, very cool, very, very exciting. Why the hell am I talking about physics? Well, space-time, forget that. The maths that went behind it was important because there was some kind of linearization problem. And they said, hey, this stuff looks complicated. Let's think about a simple example and think about perturbing it. And then let's see what we can pull out. Then they postulated that stuff like this might exist. And what that signal is the noise or the remnant of 2 black holes dancing around each other, spiraling, and coalescing and forming one bigger black hole. And the ripple, which is produced, is this gravitational wave. So it's carrying away some energy. And one part of the work that I'm interested in is actually figuring out, how do you precisely quantify the energy that's carried away from a system like that? We'll get more into the detail later. There's another tale. This is a really cheap telescope from Argos. And that's me. So, okay, this is me, I think, at age 11. If you go back like 4 years, I can find a picture of myself at 7 specifically. But the reason I put this up is because I was looking out of the window with this really cheap telescope. And I think I said to my mum at the age of 7, I'm going to see a black hole. Now, if you know anything about black holes already, it's like, the gravity is so strong that not even light can escape. So really, you'll never see a black hole. You'll probably just see like shadows or things behind it because, the light can bend that strong around things this dense and compact. But what's interesting is that as I was going through school, I kind of forgot about stars and space. I actually focused more on video games. I really liked them, and I thought I was going to make games. So I even applied to uni eventually to do computer science because I was like, I could make games, or maybe I should just do computer science a bit more generally. I don't know what I'm going to do yet. And then, of course, I changed my mind at the last minute, and I say, oh, I've just done interviews for maths and computer science. The computer science ones felt weird, but maths felt right somehow. What was interesting is that I was sick in the start of my A-levels, and I think I'm a late maths bloomer for a lot of people that I talk to. I realized that, okay, I'm sick, I'm in my bed, I reach over and I pick up this textbook because I'm insane, and that's the closest thing I can, reach. I just start reading it, and I just start digesting at my own pace. Then I realized things just started to make sense once I gave myself time, and that meant that I just needed to give myself more time than what I was given in class. So what was nice is that this little boy with the telescope didn't realize that he was going to end up doing stuff to do with space anyway, but more so as a mathematician. This is nice. So here, I just want to go for an outline of my talk, and I'll kind of weave in some personal anecdotes as we go through. But you can see the motivation section is actually the biggest. I feel like there's a lot to set up to understand the types of problems that I look at. So what kind of problems I am interested in? You've already seen this kind of modeling problem for gravitational waves. I don't work on the data side. I don't even work on the waveform side. I work on how you can think about gravitational radiation more theoretically in this way, how you can quantify energy loss from systems like this. So on that kind of spectrum. To do that, maybe it's a crash course in GR. So what's the essence of GR? Some techniques in mathematical relativity, that's going to be extremely short, and a couple of selected topics. And more importantly, why you should care. Because, okay, it's cool, right? It's cool talking about space, the fact that we can detect these things. By the way, that binary black hole system, right, this Inspire, this was 13.4 billion light years away. So not in our galaxy, but we still managed to detect it. Super, super violent kind of event which happened. But by the time it gets to us, it's super weak. The things that they have to do is measure things within 10 to the minus 15 of a proton, which is a crazy engineering feat. But what's interesting is why you should care. Obviously, if you want a job, this is a good place to be. Gravitational wave astronomy is very, very exciting, but also the mathematical techniques that go into it kind of open your eyes to how much you could do in this field. Okay, then I'll talk about what we have done both collectively as a group, as mathematical relativists, and maybe specifically about what I was looking at and what we've almost done, and possibly some future directions. Okay. So my supervisor told me to be interested. Is this good motivation? That's my supervisor, that's one. Lovely guy. And this is a collaborator. He said, why don't you just follow on from our previous paper? And I said, okay, I need like a first project. So let me take a look and let me see what's interesting about it. So the way I learned about this kind of the existence of this paper, my supervisor had a lot, and this one stuck out to me the most, and I ended up talking to his collaborator, and it starts with a story as well. It's the 1960s. Lax and Phillips, they produced a scattering theory for particle interactions using some very formal methods. So what, if you don't know what scattering methods or scattering theory is, just more generally, from the in-states, so you have some experiment, you send some particles in to interact with each other, and you measure their outstates. From the outstates, can you determine what they were? Or rather, from the in-states, can you determine what they would be, right? So this like kind of deterministic, time-dependent scattering theory is what they formalized. So it was really just, I've set up some functional analysis. Can you now use this in practice? It was very, very successful. But then something else happened roughly around the same time in the 60s. Within a couple of years, Penrose introduced conformal compactification of spacetimes. We'll go over that. And that just attaches an idealized boundary at infinity, whatever that means, to space-time. Now, if you fast forward 20 years, these two separate ideas, which developed in the 60s, they're extremely far apart. Friedlander then comes along and says, actually, you can put these two things together, and this is what conformal scattering theory is. It's the scattering of these kind of particles, or maybe it's not particles, I think it was more like waves, but from the perspective of space-time. So you've got some compactified space, you send in your particles from past infinity, and you want to measure them at future infinity. And in principle, all these waves, and in principle, this is what is being done with gravitational wave detection. As observers, we sit at infinity with respect to the event that's going on a long time ago, far, far away. So with the notion of conformal boundary, it raises this question. I spoke about how you can measure these states, but really what I want to say is actually how they are related to each other, right? So if you think about classical PDEs, right, you have this kind of determinism. If I give you initial data, you can tell me what the solution will be. And if you change the initial data a little bit, is my solution still pretty close afterwards?
You might have to just say what PD is.
Good, yeah, no, so some differential equation, but you have different dependencies in your variables, both in time and space. So those kind of equations are quite finicky to deal with. So let's just go over the essence of GR. This is mostly some stuff which is very, very important to set up the problem. So if you just want the one-line sentence, GR generalizes, right, general relativity, Einstein's theory of special relativity. Well, that needs a couple of ingredients. You've got the equivalence principle. If I'm in a rocket ship, I can't tell the difference between me being in a rocket ship and accelerating, or just standing still in a gravitational field. This is kind of like your perspective shouldn't matter where you are in space-time if you're considering these effects as the same. So, you put this together, and what Einstein concludes is that gravity is not a force, it's a property of space-time. This combination of space and time, there's 3 dimensions of space and this 1 dimension of time. So you can model space-time by a manifold, a 4-dimensional manifold. And what is that? So locally, things look like flat space. So if I'm standing on the Earth, it looks flat, but we know the Earth's not flat, right, guys? Okay, good. So we know the Earth's not flat, but that's what a manifold is, right? Locally, it might look flat, but globally, it has a bit of different structure. So that's what a manifold is, but we've got 3 dimensions of space and 1 dimension of time. That's what we're doing with space-time. So that's what that M is. Generically, it's a space that looks like Rn locally. And now what's this G? This is called the metric. It has a particular signature. So when you're dealing with vectors and inner products, the metric is just like an inner product. If you're talking about vectors and you're talking about are they orthogonal or not, that means they're going to be 0 if they're orthogonal. And if not, then it's going to be some positive number. This is not true in space-time. The fact that it's not definite anymore is actually super important, and it's a feature, not a bug. So you call points in space-time, right, as manifold events. And what you can do is you can connect events with geodesics, with little curves. And what the metric does, it provides a way of telling you what type of curve it is. So if you've got a curve or a path, you can think about how fast you move along that path. And the direction at which this points tells you the causal character. So take the tangent vector, right? Take the arrow, the speed along that curve. And if this is positive, as a positive inner product or positive norm, then it's time-like. These are like the kind of paths that us as massive observers, or even particles with mass, would follow. So you don't break the speed of light barrier. Typo. If it's 0, this is supposed to be null or light-like. That is the exact barrier there. Oh, another typo. Lovely. That's supposed to be less than 0. That's space-like. Those are forbidden. No one travels on those, okay? And if you did, then I think some people like to postulate these are called tachyons, and some people care about that, but not in classical GR. That's definitely a no-go zone. So a little bit more. Once you've got all that set up, then you can place this equation right here. this, okay, so everyone knows E equals mc squared, right? That equation from Einstein. Really, everyone should know this one. This is the one which gives us GPS, basically. So what this is saying is that, remember we said that space-time is the way which tells us like gravity is somehow a thing. But gravity is not really a force, it's just an effect of space-time. What this says is that curvature on the left-hand side, some tensors, is equal to or proportional to some kind of matter content. That's what pairs GR together. So for lots of different reasons, you can actually assume this is 0, and then that equation above just reduces to the Ricci tensor, which is just some way of measuring curvature on your space is 0. It's still very interesting and hard, because this thing is made out of lots of different derivatives of the metric. So all of your spatial derivatives and time derivative and stuff like this, and second derivatives too. So here's a couple of examples. You get the flat space of special relativity again, Minkowski. You can discover rotating and non-rotating black hole solutions from this, from that simple equation, and you can discover cosmological models of the universe. And even in this playground of special relativity, you can consider things at infinity. So this is flat space with the flat metric, which is just like, consider your normal Euclidean metric where you're just taking the dot product. Now there's a difference in sign on one of the components, that's it. What happens when nearing infinity, things are a bit complex, but we have a saving grace in mathematical relativity. Rather than take a look at the behavior at infinity on a non-compact manifold, so I look in all directions and I could go on forever, why don't we say, well, go on forever, but no matter which way I go, we consider it as going to infinity. That's like one point. So that is the idea that Penrose had. It'd be more convenient to look at a local behavior near a boundary rather than infinite behavior on non-compact manifolds. We also want to preserve light-like directions. That's how we can do detections. Gravitational waves were theorized to travel at the speed of light. This has been confirmed, so we definitely didn't want to screw that up. So here's where conformal transformations enter the game. And this should be familiar to anyone who's done a little bit of differential geometry. This is just, I can take the plane, the flat space, consider going to infinity as one point. And what that actually equates to is taking a look at the sphere. If you're at the North Pole, this is like at infinity. If you're at the South Pole, this is like staying exactly where you were and never moving. And everywhere in between, from the South Pole to the North Pole, means you're moving further away. So stereographic projection from the sphere to the plane, but if you take it in reverse, that's a conformal transformation from a non-compact manifold to a compact one. Now, analysis on compact manifolds is much nicer to deal with. You just have to rescale your fields so that you have a good transformation to deal with at the end of the day. So this is what's going on in Minkowski. You see this diagram. You have time running up the picture. This is like the physicist's way of thinking about it, but it's quite useful. So forwards in time, and you have the radial coordinate from where you're standing. Now, if you consider this outer portion, this is like, so here, this diagonal line, the light-like directions that you want to preserve. Everything above this in the white is the time-like direction. This is the space-like direction from that. If you were moving in here, you'd be moving faster than the speed of light, and that's bad. We don't want that. But now what you can do is you can take this, which extends infinitely, and you can compactify it, but you don't just get one point in infinity, you get many flavors of infinity, and you get to compactify it into a nice little picture. So what happens is, okay, there's a line of symmetry here, but then remember we spoke about that there are vectors which have different causal character, or curves which have different causal character. If you were at a time-like curve, you would end up at here, the top point. This is future time-like infinity. Or if you could travel to the past, you would end up down here at past time-like infinity. These would be straight lines in this picture, but in this picture, they sort of curve around. Similarly for space-like paths, they go to here, I naught, we'll talk about him later. And light-like, these boundaries are the ones which are important for detections. If you like, where the hell do we sit in this picture? So let's assume that this compact, object was sitting at the center of space-time right here, and we're off at infinity. But what does it look like in this picture? Well, okay, the center is still here, but off at infinity, we would be up here in terms of detection. We'd be in the future towards in terms of time, but also very, very far radially away from this thing. So because of this model, that was actually what allowed us to think about, okay, it should be fairly weak. How are we going to get the right scale so we can pick this up? So it's this kind of simple idea which actually made that possible. So skip some details here to get to this picture. This is actually where the results that we show about scattering light, or not light, sorry, scattering waves which follow these light-like directions will actually influence or can be measured at the future. So from data from the past, you can find a solution to a suitable equation, like the wave equation, and detect what you get at the future. Now, what's interesting is why the hell have I chosen the wave equation when I was just talking about Einstein's equations? And bearing in mind, I spoke about the fact that there's derivatives of the metric, which are hiding in there, and second derivatives. What's nice is that when you choose appropriate coordinates, and what's nice is if you choose one coordinate system, it should be true in another one too. That's the principle of covariance in general relativity. If you choose the right coordinates, then you can actually set up your equations as good equations, which are modeled by the wave equation. So if you cast yourself back to like a differential equations class, I tell you, here's your value now, and here's how fast you're going to move from this moment onwards. What the wave equation will tell you on a normal time slice is I can predict the solution to your equation at some later time, no matter time you pick. That's not always true in space-time. So this is actually a really, really non-trivial problem. So if you refine the blue question from earlier, it's really, how does the gravitational radiation of objects in the past, how is that related to the regularity at the future at the conformal boundary? That's really the question. So one answer is that there's polyhomogeneous behavior. And okay, if omega, this big omega tells you exactly when you're at the boundary, it's 0 at the boundary, that's what this says. Then your terms in your expansion of your solution will look a little horrible. So what this is doing is saying that as omega goes to 0, it would just drop off like this if there was no logarithmic term. What the logarithmic term does, it spoils how fast it drops off and decays. This is important for physics because if you don't know the right corrections to have, then you have no hope of actually detecting the deviation from maybe what you would hope in an idealized case. So this is like the general idea and the general thing of what happens. And in the case of a space-time which is conformally compactified, this conformal factor is the thing that gives you the freedom of squashing things together. So here, these orange lines, this is where we're pasting the data, just to remind you. But there's a problem at spatial infinity. This guy is actually a problem for many, many reasons, but one of them I will say is that normally the equation you want to solve has really good properties. But what happens is at spatial infinity, it all crosses over. As you can see, this is technically a light-like direction, and this is technically also a light-like direction. That's bad for like the characteristics of the PDE, the way that you want to solve it. That means your methods don't work anymore where these things cross over. So what do? You blow it up. So let's go back. This little corner is going to get blown up to a cylinder. So that's what's happening here. There are some special coordinates that you can choose, and in particular Minkowski, but you can also do this on a black hole spacetime as well. It looks pretty simple. So if T and R are your physical coordinates on physical space, the non-compact one, you can get this now compactified spacetime where you have a modified time coordinate and a modified radial coordinate. Except now you're really focusing on what's happening at spatial infinity. Now, why the hell would you do this? Turns out that instead of everything being focused at one point, now this thing poses no problem. And now the problem only lies at the corners of the domain, which actually reduces the complexity. Now you only have to look at 2 problem childs instead of 1 really bad one, which makes the analysis doing some using some very cool methods, actually not so bad.
Sorry, this tau, I mean, there's a hidden factor of C, which is 1.
Yes, yeah, so in the units that I'm using, everything is normalized to 1, right? So it's G equals C, sorry, 8 pi G equals C equals 1, those natural units, so yeah. You can always restore units later on just by restoring them, but yeah, this is good. But yeah, so here, this is our manifold. You look at Minkowski, and you take the flat metric on Minkowski. This is what the wave equation looks like. You just have second derivatives of all of your directions, so the time direction and your space directions, and you apply that to your field. And it turns out that you can make it so that you can pull open an old paper and use some techniques from there from like 75. And some existence theory from the 90s and a bit more recently. Now, notice there's tildes on here. This is the physical space. There's no tildes on here, so I've done some conformal compactification. There's that omega hidden somewhere. But this is what the equation looks like when it's rescaled. And you say, why the hell would you do that? This looks worse. But now you can see it. You can see exactly what I was saying earlier. This tau being plus or minus 1 tells you that you're at the future or the past. And rho equals 0 tells you you're at spatial infinity. Now remember, the problems were when you are at spatial infinity, but also at one of these 2 corners. So that's when this vanishes and these terms vanish. And that means it's an ODE, and that's actually not something too bad to deal with. If I can drop to ODEs, I will do so. And that's actually the approach here. Okay, we'll skip this. We'll skip this, they're horrible. But the theorem is exactly what you might expect. If I give you data on that small slice here, I can find a solution to the wave equation at the future, which you can effectively say, can you Taylor expand and compute the coefficients? Answer is yes, because you can control the remainder in a really nice way. And you can compute that explicitly using solutions of Jacobi ordinary differential equations, a special type of differential equation. What's interesting is that when you actually compute the components or the coefficients, they don't contain logarithms. In fact, they're analytic at tau equals plus or minus 1 and rho equals 0, so that those 2 problem children. So now here's the question. Are you paying attention? I told you there would be comprehension, right? So this is not the generic behavior. So what went wrong? So actually, you can still obtain a nice class of solutions even with nice data, not just because this is Minkowski, but because the setup is a bit too coarse. But it's probably a combination of both of these. But this is good because this is something that people hoped would be true in at least some kind of context. So we're glad we made contact with this paper. But now, skip this. But now we're doing something else. This is another collaborator. We want to release a paper from Overleaf Prism, where we are using much more sophisticated tools and techniques to analyze things at the corners of manifolds. And what that will allow us to do is, given more general data, we might be able to see exactly when the logarithms will appear at the future, given the regularity of the solution at the past. Is it smooth? Is it only got 3 derivatives? Is it continuous? Is it just about integrable? You'll be able to see exactly precisely when you'll get terms like omega to the alpha log omega to the beta, or some alpha and beta. It would be nice if this wasn't on Minkowski and it was a black hole background like Schwarzschild. I think that would be very cool. But that might be a different me problem in a parallel universe. Because, yes, this is the question I just said, because you can just ask if the setup was restricted from the beginning. So the natural geometric setup is very, very historic in a sense. This existed well before the techniques that we were using were used. And this is exactly what we're doing now. And I think this is what's making my like postdoc applications like seem decent. The fact that this hasn't been done yet, and it probably needs to be done. So this is ongoing work. Hopefully in December, and then maybe next year at some point when I'm still applying for things. Okay, here's a bunch of references. And I just want to leave you with one more thing. Forgive me for overrunning. Some parting words. So I told you I liked video games, and this one quote from a video game came up, but then I realized this was a real person. Embarrassingly, only found that out like 2 years ago, because I'm not this old. I never realized that this person was real. But anyway, here's the quote. It says, "All people dream, but what are you calling? Those who dream by night in the dusty recesses of their minds wake in the day to find that it was vanity. But the dreamers of the day are dangerous, for they may act their dreams with open eyes to make it possible." It's a quote from T. Lawrence, who I didn't know was a real person until 2 years ago. But this quote came up in a video game, Uncharted 3, if you're interested. And this was the quote that I hung up on my bedroom wall at 16, when I said, it seems like if you just work hard for the things that you want, and you have the correct support, so thanks, Mum, then the little boy with the telescope can still do physics and maths. I think that's what I wanted to leave you. Any questions?
Great, thanks, Jordan, for that nice talk. Yeah, any questions?
So you said that with the LIGO experiment that we didn't detect anything for like 25 years.
Yes.
And then the first thing we detect is some faint distant signal like very far away.
Mhm.
Is there anything particularly in the maths that sort of explains why we're not hearing things nearby? And, or is that just like an experimental thing?
So yeah, there's a couple of reasons for this. That's a good question. There's a couple of reasons. So the engineering hadn't caught up yet to the theory that they put in place. In fact, the design for LIGO was as early as the 70s. They got the money to start building it in the 90s, and then they realized they need to catch up on the engineering. That was one part. So they improved the engineering a lot very, very quickly. Mm-hmm. The second thing is that the calculations showed that if you were going to detect any kind of gravitational wave signal, it would be tiny by the time it got to Earth, because some of the closest systems that we now know of aren't actually that close. It is still on the order of like tens of billions of light years. Even looking at supermassive black holes at the center of our galaxy, like Sagittarius A star, we're still not sure of its properties because we haven't got good enough like handle on the asymptotics of these kind of things. So I work at like the super extreme end of the theory, but this does trickle down and translate eventually.
So it took like two really massive black holes to produce a signal that you'd be able to pick up, or can
They
you, like,
were
pick up, say, like a rotating black hole or something?
This is a good point. Yeah.
Survive.
So they don't need to be super huge. So they are now able to detect black holes which collide of mass, well, as low as they can go effectively, which are like 5 times the mass of our sun. I think GW 150914. So the first one was 2 about 30 and 25 solar masses. So they're pretty comparable, but a lot bigger than our sun. So those were black holes that collapse. Our sun will not collapse to a black hole. It'll swell up and then fizzle out.
And how far away were those black holes, like out of the galaxy still?
Yeah, out of our galaxy.
Oh,
yeah. Yes.
So yeah, very nice talk. So in terms of the, so if you go back to where you sort of showed this wave equation, with this eta and so on. Good. So I mean, we're assuming you're observing this sort of gravitational radiation in a sort of flat space. So the observer is in some unperturbed space.
We're at this idealized point at infinity. So I'm working on exact Minkowski here. But if I was probably a bit clever in hindsight when I started, I probably should have worked on a more general class of spacetimes, which just say you are not exactly Minkowski, but as you get to infinity, you approach Minkowski. And then the story is very, very similar. So even doing it on exact backgrounds gives you a big smoking gun as to how you would do it in more general spacetimes.
Yes, it's actually, so building from that, this actually might be, because it's not my area, but so on the right hand side is 0, but you could imagine some source.
Precisely, yeah.
So if I have some epsilon source, is that interesting?
Yeah. So interestingly, if you want to prove the result that we did, you have to consider this equation with some like appropriate vector at some point. Okay, great. But what that does is when you start to shuffle things around in a horrible equation, which I skipped over, then it produces a source term that you have to control anyway. So if you start with a source, you're going to have another source. If you start with 0, you're going to produce a source anyway. So then it's just what assumptions you put on the source when it does get generated. And as far as I'm aware, there are no bad assumptions in that sense because they're like experiments focused in the way that it's given. So
nice. So we have one question from the Zoom. I'm just reading it before it makes sense. So does gravity fall in the same category as space, time, and light in terms of relativity?
Yeah. So in terms of the speed at which they propagate, yes. In terms of being extremely hard to work with, yes. Because, you know, the discovery of a thing which we thought as a force carrier for gravity found does exist. But when you're considering it on large scales, you don't think about it like that anymore. You consider it as a wave, which is exactly what you do when you think of light. At small scales, you think about it as a wave packet. At large scales, you want to think about it as electromagnetic radiation. So they're very similar, but they have their differences.
If I may sort of draw some random things. So I guess Einstein ended up with the right equations for GR around 1920. I mean, he took to write just before. And of course, it's just approximately 100 years ago. So, you know, reflect on that, right? So you're working on something that's like an actual theory that's very old, and then, you know celebrating Albert Cox is 100 years. Got his PhD 100 years ago. So comment on that.
Yeah, I think the fact that there are still questions we need answered in GR kind of makes me think how crazy Einstein was, but also at the fact that he stumbled onto something which no one at the time, not even him, knew the full extent of. He didn't realize that he was going to make GPS, for example, but he did predict gravitational waves. So it's very interesting how, you know, you change your perspective and it gives you something, okay, maybe more useful in a day-to-day life. But the fact that we still don't understand enough, for example, as to how to extend GR is also a problem. We have tests of GR to see when GR fails so that we can pick out the right new theory, and then I'm out of a job. So
yeah, that's true. Yeah. That's just funny. So you mentioned GPS, but there is a famous, I think she's a black woman, right, who studied geostationary orbits, Gladys West. Yeah. So another black hero. But let's thank Jordan for that excellent talk.